Okay. Uh, Looks like I'm going to talk about the graph labeling, but I'm going to start with a disclaimer. There are so many graph labelings, about 200 different techniques. We're going to talk about only graceful graphs, magic graphs, and super magic graphs. It's just a taste of what the graph labeling is about. And also, I wanted to apologize also. This presentation I prepared as if people don't know anything about graph theory. So I apologize to those people who already know graph theory. Okay. So let's start with what is a graph? Well, obviously this is one kind of graph, bar graphs, but that's not the graph that we're going to talk about. Here's another graph. Very neat graph. Graph of a function, certainly, but that's not the kind of graph we're going to talk about. So what kind of graph are we talking about today? Here it is. Graph is a finite collection of vertices and set of edges that are made up with unordered pairs of vertices. And we are going to call the V of G as a vertex set, E of G as an edge set. So, well, let's look at the example. Suppose we have 5 vertices, A, B, C, D, and E, and edge set contains pick 2 letters, for example, A and C, C and D, AD, EC, BD. So this represents actually one edge. First edge connecting vertices A and C. Second, C and D. Third, A and D. And E and C, B and D. However, it depends on how you label vertices. We may have the same graph but drawn differently. A and C, C and D, AD. As far as the graph goes, they are identical. We call that isomorphic. But it's simply drawn differently. Okay, so now let's look at some classes of graphs. Complete graph, which is denoted by capital K sub n, is a graph that contains exactly one edge between every pair of vertices. So obviously, K1 doesn't have any edges, K2 has one edge, K3, K4. By the way, there are 4 vertices. This is not a vertex, that's just the edge crossing. And K5, 5 vertices, and then there are 10 edges altogether. Okay. So that's one kind of class of graph. Second kind, complete bipartite graph. Split the vertex set into 2 groups. First set on the top, second set on the bottom. So for example, if we look at the K sub 3, 2, there are 3 vertices on top, 2 vertices on the bottom, and each vertex on top is adjacent to or connected to every vertex on the bottom. Okay, and here's K24. Cycle is kind of obvious one here. Vertices in circle manner and then connect a pair of edges in cycle manner. Next one is wheel graphs. Basically start with the cycles and put a vertex in the center and connect this vertex to every vertex on the cycle. It becomes a wheel graph then. Okay. Fans. Interesting name. Okay. Start with a path, if you want to think about it, and then add one additional vertex and join this vertex to every vertex on the path. And the subscript n basically counts the number of triangles. So this one is a 1, 2, 3, 4, 5 triangles. So this is an f sub 5 in the case. So, by the way, each triangle is called also blade of the fan. Here's an interesting one. Bernoulli family. They are somehow, one way or another, involved in mathematics. And just like Professor Dersch mentioned earlier, I'm going to mention the famous Euler's name here. Daniel was friend and colleague of Euler, and Euler studied under Johann first. Okay? So, obviously, if you look at this, this represents a family tree. So we're going to look at the class of tree. Tree is a connected graph that contains no cycles. And if we represent each person of Bernoulli family by vertex and join the two vertices by relationship, father-son relationship, that becomes an edge. So here is the Bernoulli family tree. And this is just, going backwards. Ordinary tree there. And sometimes we may find these things next to the tree. Okay. And still, this is considered a tree because there's no cycle and connected. Okay. All right. So, starting with the vertex labeling, we're going to focus on the graph, graceful graphs. In this case. Rosa, in 1966, published a paper on certain valuation of the vertices of graphs, and this is the beginning of the vertex labeling. Suppose we have graph G with p vertices and q edges. Function from vertex set to set of integers, 0 to number of edges. That function is called the beta valuation if function is one-to-one function, such that when every edge connecting the vertex U and vertex V is assigned with a label absolute value and the difference of the function values. Now, I'm going to explain a little more. Right now, it's very technical. When we do that, every edge gets the positive integers from 1 through q. Okay. That's very technical. But 1972, Solomon Golom published a paper, How to Number a Graph. And then he started calling that beta valuation graceful, and from that point on, it is now called a graceful labeling. So, loosely speaking, what was in the previous slide, graceful labeling is an assignment of distinct non-negative integers, so including zeros, to vertices of graph G in such a way that each of the q edge gets a distinct positive integer from 1 to q as the absolute difference of the number on the vertex or vertices. And we call graph graceful if there is a graceful labeling. I think we should look at an example of that. So, here are 3 conditions. Use distinct non-negative integers, 0 to q, to label the vertices. And then take the absolute difference of the numbers on the vertices to label the edge. And all of the edge numbers should be 1 through q. Okay, so here it is. This has 5 vertices and 8 edges. So we could use a 0 through 8 to label those 5 vertices. it's 0. And the absolute difference is obviously 1. Let's label that one 2. Absolute difference between 0 and 2 is 2. Okay, now we have a 0, 1, and 2, so let's label this one 8. Then absolute difference would be 8, 7, 6. And label the bottom one as 5, and the absolute differences are 5, 4, 3. So we use the 5 integers from 0 through 8, and when we label those numbers, absolute difference is 1, 2, 3, 4, 5, 6, 7, 8. Okay. There is another way to label this graph. This one is what we call the complement labeling of that one, basically. All right. Starting with the first class complete graph, K sub n. How do we label them? Well, K1, that's it. There's no edge to worry about. Done. K2, label 0 and 1. Absolute difference is 1. We are done. K3, 3 edges, 3 vertices. So far, so good. K4, there are 6 edges, so we could use a 0 through 6 to label the vertices and find the absolute difference. So, complete graph up to 4 is okay, but Solomon Golom says after that, it's impossible. No matter how much we try it, we cannot label the vertices so the edges gets 1 through number of edges. Next, complete bipartite graphs. That was easy. How about this one? So this one has 5 vertices and 6 edges. 3 times 2, there are 6 edges. And here is label the vertices 0, 1, 2, down 3. Now the absolute difference would be 1, 2, and 3. Label the other vertex as 6, and then absolute difference would be 4, 5, and 6, and that's graceful. Next one, for complete graph 4, 4. So hopefully you see the pattern here now. Absolute difference is 1, 2, 3, 4. The next one jump to 8 as a label. And so the absolute difference is 5, 6, 7, 8. Next one would be 12. And absolute difference is 9, 10, 11, 12. And finally finish with 16. And we have this labeling. So basically that starting with a 0, those vertices on top, label them with how many there are, 0, 1, 2, 3, 4, and so on. But then multiply the denominator, the bottom vertices over here by number 4 in this case. Here's a general idea. So suppose there are m vertices on the first set on top, and there are 0 through m minus 1. And if I label this one as an m, difference between this is 1, difference between that is 2, so on, and difference would be this one, and 0 is m. Okay. Increase the second vertex as 2m, and this way. So this gives an idea how to go by labeling complete bipartite graph, and certainly Solomon Golomb again said complete bipartite graph is graceful for every M and N. Cycles. So this is two are graceful. How about C5, 5 vertices and 5 edges? So we have integers 0 through 5, labeling 0, 5, 1, 4. So that leaves only two numbers, 2 and 3. Regardless of which number we use, 2 or 3, it is impossible to have two different numbers in this case. Okay. Once again, we are stuck on this one also. Two numbers remaining. They are 3 and 4. If I use a 3, difference is a 3 here, and difference is 2, so 3 will be repeated. If I use 4 here, difference would be 4 and 2, and 4 will be repeated again. So these are two are non-graceful. C7, yeah, we could do this one. And here is a graceful labeling. Cycle with 8 vertices, yeah, we could do that too. Seems to me there's a pattern. 2 consecutively is working, 2 consecutively is not working, and so on. And it was proven by Rao Hebare. If cycle has a multiple of 4 vertices of multiple of 4 vertices or 3, addition 3, then it's graceful, but the other 2 cases are not graceful. And then he said that, well, what about wheel graphs? Are they graceful? And Frucht answered that question. All wheel graphs are graceful for n greater than or equals to 3. And to show that, I wanted to show you both fans and the wheel graph at the same time. So here's the fan. To label the fans, use the 0 and then odd numbers on the outside. And then next one, 7, 5, 3, 1. And we have this labeling. Okay. So as I said before, wheel graphs and fans, the only difference is that one of the edges is missing in the fan. So going from this one to that, how do we label? Everything will be same up to this point. As you can see, 1053, 1053. But because we added extra edge over here, we need to somehow change those values, and here it is. Now, difference is 1, difference is 2, 3, 4, 5, and 6, and that's graceful. How about next one? Well, start with graceful leveling of fan, and then change these two numbers. Okay, same thing as this. So to generalize this graceful leveling of fans and the wheels, start with center vertex as 0 and outside will be just the odd numbers. Same thing, center will be 0, outside will be odd numbers. And when we label the wheel graphs, increase this number by 1, but increase this one by this number n minus 2. However, if n is even, then increase this one by 1, but the other one stays constant as a 2. And if you go back to the previous, when the n is even, the right side number is always constant 2 in that case. Okay. All right. The class of graph that got most attention is the trees. And here is the first few trees with graceful labeling. And 5 vertices have 3 different trees, and graceful labelings are given here. Well, Gerhard Ringel said it doesn't matter how large and how many different trees there are, every tree is graceful. And the thing about that is, it has not been solved yet. It is a still open problem. And people have been trying to prove this thing for last 50 years, and no one has come up with a general proof of that. Some of the other trees are already proven. Paths are graceful, caterpillars are graceful, canary, that's just like a binary trees or trinary trees type of things. And symmetrical trees are graceful. And also, using computer, I think they have proved that all of the trees are up to 35 vertices are graceful. That was as of December, last year, December. Here's a couple examples here. Paths, just straight lines. How do we label those things? That's it. Caterpillars. Starting with by the way, this one has 20 vertices. 20 vertices. And these are considered, outside ones are considered the neighborhood of this vertex 0. And we could label them with 19 through 15. And then increase next one by 1. And then we have 1 has a neighbor 15 through 13. This kind of trees are already proven to be graceful, and here's a binary tree, and that's also graceful. Difficulty trying to prove that all of the trees are graceful. I think I showed you only up to this one. Tree with 1 vertex, there's only 1 of them. 2 vertices, 1 of them. And I showed you 5 vertices, there are 3 of them. From that point on, number of the different trees grows very, very fast. And so far, we have up to this point, which would be 2,262,000,000,000 different trees to consider. So there is no unified method for labeling all of the graceful, all of the trees at the moment, but divided them into class by class, smaller ones. So paths are graceful, caterpillars are graceful, canary trees are graceful, and the symmetric trees are graceful. Okay. Labeling the tree is helpful in graph decomposition, and obviously trying to split the graph. Easiest way is to split them into single edges. Well, what about using two edges? So here's the K5. Can we split it using two edges? And here the answer is yes. There is. What about cycle? And you may say, that doesn't look like a cycle. But if we untangle these graphs, it eventually becomes something very similar to this one, actually. So these two are, we consider as a quote unquote same graph or isomorphic graphs. Gerhard Ringel once again said, if T is a tree with a Q edges, then complete graph K sub 2Q plus 1 can be decomposed or split into 2Q plus 1 copies of tree, of that same tree. This is still unproven. And then, few years later, breakthrough. Rosa said, if T is graceful, we could do this. We could prove that. So now, Gerhard's Ringel conjecture is depending on whether T is graceful or not. So up to this point, Ringel's conjecture is true for all of the edges of the 34 edges of trees. Okay? Here's a couple examples. K7, we could split that into 7 copies of tree with 3 edges. Another example, same case of 7. Seven copies of another tree with 3 edges. All right, let's move on to the now edge labeling. Given a graph G, an edge labeling is an assignment of integer to every edge of graph G with a certain condition, and the condition that we're going to talk about is the magic and super magic graphs. Magic square. Here's a 3 by 3 magic square, and obviously if we add the numbers on the first row, second row, third row, first column, second column, third column, or diagonals, they're all same, 15. And here is a diagram for the earliest known magic square. (1963) at a conference, Jiří Sedláček published a paper and asked the question, could the magic idea could be applied to the graph theory? And some people ask questions. Usually mathematician tends to answer those questions. Madison Stewart is actually not far from, he was not far from here in Michigan State University, professor Michigan State University, published a paper called Magic Graph, and then same year, also Super Magic Graph on complete graphs. And he defined what it means by graph to be magic and super magic, along with a few other terminologies. Okay, so what is a magic labeling? A connected graph G is called magic if there is a labeling of edges with a distinct positive integer such that for each vertex V, the sum of the labels of all edges connected to that vertex is the same for every vertex. I think we need to look at some examples here. We are going to now start with labeling edges. This vertex is connected to that edge, so if I add 1, sum is 1. That one is also 1. Yeah, every vertex has the same number, so it is magic. Next, using two distinct integer, we label the graph, but this one, sum of the label on edge connected to is 1. That one would be 2, but we have this one, 3. They are all different, so this is not magic. Here's a graph with the following labels on it. 9 plus 7, 16. 9, 5, 2, 16. 2, 6, 8, 16. 8, 5, 3, 16. 3, 6, 7, or 7, 6, 3, 16. Sum is the same for every vertex, and so it is magic. And this is the graph for hexahedron or cube. And this labeling is, by the way, by Stewart, same person. And I think this is really nice. Notice the numbers. Using only prime numbers at every edge, come up with another prime number, 83. And then he also gave a magic labeling for fan graphs. So here's a F sub 3, 3 blades, 3 triangles if you want to think about it. 1, 2, 3, 4, 5. So if we add these 4 numbers adjacent to that vertex, we have 12. So in order to have 12, I need to label this one 7, and that will give us the 12 on both of them. Again, in order to have 12 on this, I need to label that one 8. So that's magic now. How about F sub 5? Say 2, 3, 4, 7. Now skip to 9 here. The reason is that the addition of those two numbers is has to be same as this one. Because remember, that's the edge shares this vertex and that vertex. Sum of these 6 numbers is 26, so in order to have the sum 26, I need to label that one 17. So these two vertices would have 26 now. 18, those two vertices would have 26. 19. And you see the pattern now, what's going on. And notice the subscript number is 357. So she said, fan graph is magic if and only if subscript number n is odd. Okay. What about the complete graph? Well, this is magic. Triangle, or case of 3. We have to label using 3 different numbers. And when we look at the sum, we have different numbers. So this is not magic. Same thing, using 6 different numbers to label edges. 10, so far so good. But this one is a 12, so this is not magic. What about K5? I wanted to show that, okay, if we impose these 2 graphs, we get K5 here. So if I label this one 1, 2, 3, 4, 5, the sum on the vertices is so far 4, 5, 6, 7, and 8. I wanted to get the total sum to be 28. So I need to increase this one by 22, increase this one by 26, and so on. 24. So now I have every vertex is 28. In order to get 20 on this particular vertex, use these 2 numbers. In order to get to 23, now I need 11. And here is magic now. Superimpose those 2 graphs. And Searle again said that the complete graph is magic for all n greater than or equal to 5 and n is equal to 2. 3 and 4, as we saw earlier, they are not magic. Okay, now moving on to super magic here. So what's the difference? Super magic is using consecutive integers. We saw this graph earlier. This is a magic with a sum equal to 16 on every vertex. But we didn't use consecutive integers. We skipped number 4 in this labeling. Okay. However, same graph, let's label 2, 3, 4, 5, 6, 7, 8. So we have used the consecutive integers. 8 plus 6 is 14. 6, 5, 3, 14. 3, 4, 7. 3, 4, 7, 14. So obtaining the same value at every vertex, but using the consecutive integer is called supermagic. Okay. K2 is both magic and supermagic. Yeah, just one edge. Yeah. K3 and K4 are not magic. If it is not magic, it cannot be supermagic. K5 is magic, as we saw. However, we cannot use 1 through 10 to label the K5, and it's not super magic. And Searle proved that. And then he goes on to prove that the complete graph with a multiple of 4 vertices cannot be super magic. Why? Because in order to label the complete graph with n vertices, sum at every vertex should be this number. However, this number is not divisible by 4 when n is equal to 4 times the k. Okay. And then he gave super magic labeling for K6 and K7. With the time that I have, I'm going to just show you K6 only here. And then he goes on to state, okay, we could find a super magic labeling for every complete graph larger than or equal to 6, as long as that number is not multiple of 4. Okay. All right. Next, the supermagic labeling deals with a complete bipartite graph, and that's probably interesting to magic squares. So here's a connection. This is a complete bipartite graph of K sub 3, 3. 3 vertices on top, 3 vertices on the bottom here. And I'm going to label them in this way. Starting with 1, go all the way to 9. Blue vertices on top represents the rows. Red vertices on the bottom represents the column. Row 1, first vertex on top, 294, that's this number. Second row, 753. Third row, 618. And then bottom are the column numbers. So column number 1 would have 276. Yes. Column number 2 and column number 3. If we add 294, the sum is 15. 753, sum is 15. 618, sum is 15. 276, sum is 15, so on. Since we have same number on every vertex, the sum is 15, it is a super magic. And here is a magic square. K4, here's 16 edges, so we're going to number these edges with 1 through 16. So first row would get 1, 15, 12, 6. 1, 15, 12, 6. Second row would get 4, 7, 9, 14. And the sum would be 34 on every row. And similarly, column. All right, K5. We're gonna have to look at this one. Graph and also magic square separately. So first row, we're going to label 3, 24, 20, 11, and 7. And here is the first row number. Second row, and the sum is equal to all 65. And in this case, some of the rows and some of the columns numbers are all 65. Well, we already know that there are magic square for n by n magic square for n greater than or equal to 3. That means that now we know complete bipartite graph is super magic for n greater than or equal to 3 also. As I said, I just touched on the 3 labeling techniques: graceful graphs, magic, and super magic. Joseph Gallion, former president of Mathematical Association of America, have been collecting all of the papers, any paper related to graph labeling. He has been kind of organized them, and in his paper called the Dynamic Survey of Graph Labeling. So far, 200 different graph labeling techniques were studied, and over 2,000 papers were published on that topic. So if you are interested in deeper study on the graph labeling, you probably wanted to go into that source. To go. Okay. some of the application of graph labeling here: coding theory, X-ray, radar, circuit design, communication network addressing, and database management. So that is the, I'm looking at the time here, topics that related to the graph labeling. Now I'm going to give you a little bit of bonus talk here. 2014, 2015, GRCC is celebrating 100 years, and our department chair asked us to find some ways to obtain the number 100. And I thought, all right, let's look at the graph. Who gives a sum equal to 100? And I'm going to call that GRCC Centennial graph. Okay. And we want every vertex has exactly sum equal to 100. Remember that magic graph? Very simple one. Well, so how do we get the GRCC Centennial? Increase this label by 99. And here's a beautiful, elegant, simple GRCC Centennial graph. How about this one? This one was a magic graph with every vertex has sum 28. So how do we make the GRCC Centennial? I want every vertex to be 100. That means the difference is 72. 72, but there are 4 edges. 72 divided by 4. Increase every edge by 18. So 1 becomes 19. 2 becomes 20. And here is a GRCC Centennial graph. How about this one? I could not find it. There's no way I could use the all prime number to get 100. I have to use 3 numbers. There are exactly 3 ways to get the 100 using prime numbers. Okay. So I decided, okay, I could use 2 of them. And the rest of them, I just fill it in. And if you notice, there are 3 composite numbers, and rest of them are prime numbers on this one. Composite, 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 and rest of them are prime. So cube graph is also GRCC Centennial graph. Remember this? K55, which give us the 5 by 5 magic squares, okay? And the sum at every vertex is 65, but in order to make the GRCC Centennial, I need to increase by 35, right? And since there are 5 edges, 35 divided by 5 is 7. Increase the every edge by 7. And we have this. So this is a GRCC Centennial graph also. Of course, if we have this, then we could have 5 by 5 magic square also. Increase this one by 7. And the sum at every row is 100. Sum at every column is 100. Even the diagonal turned out to be 100 also. Yeah. And this is the one I think you see in the mathematics department banner.
I'm crushed.
You're crushed.
You did not ask me to bring the banner.
Oh, I'm so sorry.
I would have been honored.
Yeah. So, well, here we go. Thank you. That's the end of the talk. And so.